Well, I think we're about there. Welcome back, folks. Looks like so far it's a Zoom only class. Nobody's here in person. Hopefully we get a couple more people to join in a few, as we get started. But before we do start, any questions at all to begin with? Okay, just a quick rundown of the announcements today. We are nearly done with section 7.3. We would have finished it last class meeting on Monday, but something went wrong with the live coding session we were trying to achieve, which is, in a certain sense, kind of normal and ideal in a way. It's normal to have a live coding session like this, kind of goes sideways, that things go wrong. Then recovering from that is a good skill in and of itself. You can imagine even in an interview process, you might be asked to do a particular live coding demonstration on your own. And if things go wrong, if the syntax doesn't run, that's part of the interview. The interviewers would want to know how you handle that, how you problem solve through it, those kinds of things. So we'll hopefully finish the code here in section 7.3, after which we'll move into the bigger section 7.4, where it starts to take everything together, including an extra operation with the modular arithmetic doing division. Not exact division, but multiplying by a multiplicative inverse. Well, that's what we're working with so far today. But the bigger announcement is that our exam 3 is also going to be next Tuesday. The brief rundown on what's going to be on the exam is for section 4.4, we're going to prove that a function is a bijection, so 1 to 1 and on to. Not a crazy function, it's more about the proof methods, not intense algebra, that kind of stuff. 5.2 is going to be doing an induction proof. This can be anything along the lines of what you saw in the homework, anything along the lines of the versions you see here in the sample exam set. But it's going to be kind of a problem where you'll deal with a summation formula or a divisibility formula, one or the other. We made a big hint on 5.3. That's the strong induction section. In the strong induction section, we're going to do something similar to a problem that we did on the lecture notes and the exam or the homework as well for 5.3. Last problem on 5.3, we had to implement a so-called Lucas sequence into pseudocode. Then we had to prove using strong induction that the pseudocode would run and give us the nth term of the Lucas sequence for all n. So we're going to go for a problem kind of like that one. It's going to be sequenced just as before and pretty easy to handle like the one on the homework set. But I feel like that's going to be the tougher question, the one where we have to be aware it's coming up to make it a fair exam. So take a look at how you solve the problem in the homework. Any feedback that I might have given you, you might want to ask about to clarify if necessary, and I'll be happy to help out. And there's other versions of those same kind of problems here and here. I'm going to be working on solving these starting on Friday, hopefully getting it posted before Friday afternoon. Lastly, section 7.2, we're going to do a couple things. One of them is going to be using the formulas in section 7.2 on modular arithmetic, adding, subtracting, multiplying, and exponentiating to just break down certain problems, make them simpler to calculate mod n, whatever the n value might be. And another problem is going to be similar to the section 7.2 homework, where we'll trace an algorithm, probably the mod and div algorithm or the Euclidean algorithm, nothing with really, really heavy recursion that we already had to deal with in the homework set. But be prepared to trace any one of those algorithms only from section 7.2. So that's
Will
what's
the
going to be
will
on
the
the
code of the
exam.
algorithm be prepared or provided on the paper?
Yeah, absolutely. Here's how it's going to be provided. Thanks for asking about that. It's going to look pretty much like this. So I'm thinking either the mod and div algorithm, it's somewhere over here. So it's going to be provided as a picture on the exam exactly like this. It's minus the color coding. So you'll think of this as being the pseudocode. If you like, you could write it out a little bit more descriptively, but this pseudocode would work just fine for tracing a mod and div. I'm not going to give a special case where n is negative, so you had to do the else part of the block. It'll be kind of just a standard trace through this. And then if it's not mod and div, it could be, let's see here. I think I'm going a little too far. No, it could be this one. This is the right one. The standard Euclidean algorithm but not with lots of different recursion. So either this one with just one recursion, there are several recursions in the homework we had to deal with, similar to the one that's on this problem right here as well. So yeah, if it's this one, there'll be just a screenshot like this directly printed on the exam showing the method. Other questions about that so far? Okay. And like we mentioned, this is going to be the very last page of the exam. And where was I going with that? Oh, and of course, in the last page of the exam, one of the last problems in section 7.2 is going to have us use properties of modular arithmetic. Just like it stated in the homework, we need to show steps actually using these properties. It's a big part of what chapter 7 is all about, modular arithmetic with number theory. So there'll be a problem where you have to use these properties right here, but nothing too far out from what we actually did in the lecture notes in 7.2, and you did as well in the homework set. I'll be working after I get the solutions posted to this on grading the homework, getting it all sent back so that you have access to all of these sets right here as part of your studying. And if any one of these went late, I do accept them for full credit. That's probably the first thing you should do as your preparation or exam 3. Studying for the homework is the best strategy. If life got a little bit busy and you're late on any one of these, that's the first thing that you ought to do. Well, any other questions or comments about the exam 3? Okay, what we'll return to now is the Chinese remainder theorem. This one was pretty rough. It must have been just not in my most awake state when I tried to get through this on Monday's class. But we did a pretty good job, actually. I looked over the pseudocode over and over again, and I really couldn't find an error to this. But maybe just a quick reminder of what the pseudocode is trying to achieve. We're trying to implement the Chinese remainder theorem, but now the general version, which is going to solve k different congruence equations. So we'll just call it a system of k congruences, where x mod ni equals ai. The values for ni and ai will change according to this subscripting right here. The way we solve this problem is we feed it back to the Chinese remainder theorem for specifically two congruences. That's a problem that we were working up right over here. We managed to get this code to work right. We're able to solve x mod 5 is 4 and x mod 11 is 7, so a system of congruences. By calling Chinese remainder 2, we input the values coming from the mod side into the equations as the first two inputs, so it's a 4-input function. Then we input the right-hand side of the equation as the last two inputs, and this correctly gave us 29. Double check showed that that was the right value for this. But then we worked really, really hard on this pseudocode and it didn't give us the right value. But first, the idea with this pseudocode is we want to use this Chinese remainder theorem here, special case. So if there are any equations right here by the red dot, that means we want to pass a vector into this function. So this vector is going to contain all of the mod parts in the equation right there. Next, the right-hand side's ai, we called an a vector. It goes right inside there. And we need to plug these back into the Chinese remainder theorem. But it only accepts, let me put my fingers up right, 4 inputs. So when we go to run this right here, we're going to first pass in an n and m. That comes from n vector. We're going to initialize before we're inside the for loop, n vector 1. So that would be the n going in. Then once we're inside the for loop, we initialize at 2. So this is n vector 2, just the second mod part in the system of congruences. But n vector 2 goes in there for m. Likewise, we do the same thing with a vector. Calling it 1 right here is giving us the a that goes in, Chinese remainder theorem special case. And then down in the for loop, right over here, initialize at 2, and we get the b vector going in. Just matching up a bit of color coding there. So all that has to go inside this algorithm right here. And that's what this line was attempting to do. Chinese remainder 2, we put in the n current value coming from up here, the n next value coming from the loop, then the a current and the a next, those are both the right-hand sides for the last two inputs. First two inputs were the left-hand portions by the mod part. So this should run correctly. And once we do that, we reduce the system of congruences to k minus 1 congruences. We update the for loop by putting in n new equals n current times n next. A new is just the value of x that would have been returned right here on the original algorithm. But now we're treating this as a new x, a new value right here, ni, defined in this way, n new. And now we have k minus 1 congruences. We're just going to loop through again, feed into this statement here, the next pair of congruences. And then we just keep on doing that until we return a current. This is returning now just this part, x, which hopefully solves all congruences. It failed to check that when we gave it a try, but that's the idea of this syntax. Then down below right here, we have to reinitialize what a current is, n current, by redefining in the new values so that when we loop through again, we're putting in those new values through right here. Oh, yeah, here and here. So now taking a look in the pseudocode, here's was our best attempt to run it at the time we had before running out of time on Monday. There is an error here. This is, hang on. This is not quite the pseudocode we ran out. There's an error here somewhere, but it looks like I fixed the error before class. That's kind of unfortunate. That takes away the fun out of this. Let me do one thing very briefly. Let me fix the error, bring it back to the way it was. Sorry about that. I really did want that error to be in just the way it was. Okay, now we've got that fixed. The syntax is broken, and it's our job to find out exactly where. There's no way I was going to spot this in class because it was my mistake. And when I make a mistake like this, it's like the error is just totally invisible to me. I need another set of eyes, or just take a break and come back to it much later, which is what I eventually did. So here's the theorem. The pseudocode that it's tempting to match up to is on the left. Let me reframe this better. Anyone see where the breakdown is in the syntax so far? While we're thinking about that, just going to double check what I've initialized in here. I want to rerun this function because I ran it in the correct way with the fix. Okay, the function's now been updated to not work correctly, but we'll fix it very shortly. And again, while we're thinking about that, let's take another look at what went wrong when we tried to call it. When we called the flawed function, Chinese remainder theorem, so this is the full version, we have to pass to a vector of the mods. So we'll go C, lowercase c, there's caps lock, there you go, lowercase c to combine and get a vector, 3, 5, and 7. Then the next vector, that's the one we call a vector, we combine that to get C, 1, 2, 3. And that's not what it gave us the first time we ran this, I believe. We got a 0 this time. So the code seems a little bit, the syntax seems a little bit more angry. Something's definitely not right here. It's really hard to spot what's wrong. So 0 wouldn't solve these. 0 mod 3 is going to be 0, for example. So up here, anyone happen to see so far where the breakdown occurred?
I'm looking, but I haven't seen it yet.
Yeah, I hear you. It's really kind of subtle. It turns out it happened right inside the for loop. Right inside the for loop, the first thing I did wrong was when I ran this the first time, I put 2 here, 2 here, and we had to fix that. We had to realize we're actually running an honest for loop. So index I has to occur inside these. But then comparing really carefully on the for loop on the left, we have to have nx equal n vector I. This is pretty much what I did after class. I was reading through these line by line, trying to spot the breakdown. That worked. Then I looked into A next,
Oh,
A vector I, and I read right through that. That looks like A vector I to me. Probably because it's just my expectation it should be there. I never noticed the error, but it's right there. At least that's the claim. Let's run this, see if it runs correctly with A vector I. But does that make sense to folks on where it went wrong?
yes, sir.
Awesome, I'm glad to hear that. Let's run this again. So now the function's been reinitialized. I was a little nervous that it outputted a 0 that time. In class, it outputted a 70. So let's see what the behavior is now. So we're going to feed in this system of congruences into the Chinese remainder theorem. You know, we've already ran that. The little trick here is oftentimes you can hit up arrow to just recall your last thing. So here's the call for Chinese remainder theorem for the system of congruences. And it gets us an 87. That's not what I was expecting on this. Let me see what could be going wrong on that. So we have all of our algorithms in here. 87 coming out is totally flabbergasting to me. Let me take a look into my rewrite on this function.
Is
So,
up above where it has N current and A current, should that be A vec on the second line?
oh, good call. It's a mistake right here as well. That's one I absolutely did not see this time. I was flabbergasted. Good eye on that, Michael. It was exactly right here as well. Looks like that mistake was made twice, but I never noticed when I looked into this syntax. Let's try it again with A vector at 1. Good eye on that. Let's hit Control A. So now it's ran again. Up arrow recalls information from this system. And that is what I was expecting. I
Nice.
think we got it, folks. We have now a 52. The algorithm finally works. Some people mentioned that they solved this without the algorithm already on their homework set. I'm not too opposed to that. So if you've got the solution to the system, I'd say that's great. But now any system of congruences that could be put on the table, we can solve really fast. First, let's finalize this one. Our claim is that x has to be equal to 52. That's the only thing we can put here, here, and here to solve the system. And we can look into that pretty fast, say for x mod 5. 5 goes in there 10 times, remainder 2. That looks about right. But for the other ones, we might as well treat ourselves to the algorithms we've been slaving over. Let's call mod and div. And we want to take 52 mod 3. Bracket 1 is just going to give us the modulus operation. We get a 1 as expected. Then down the line, I guess we've done this one, but let's do 52 mod 5 just for emphasis. We get a 2 on that one. And last, 52 mod 7 gives us a 3. So we finally have a working Chinese remainder theorem. Thanks for your patience and help with that so far. I'm getting through this one. I think this is going to be the roughest algorithm in the entire course. But any last questions, folks, on getting through this one here? Okay, I want to do one quick check. We're dumping all of our algorithms right here in chapter 7 and moving the folder down as we go through the notes in chapter 7. I want to make real sure the one I shared right here is the correct one, now that I spotted a second error there. So we need to have, let's take a look. N vector, A vector, N vector, A vector. Okay, I think this one is supposed to run as intended. So this is the code that's shared, slightly different than what we did here, but I think mostly pretty much identical. So let's go back to where we're at. We're now in section 7.4. Let me save these notes up and we'll take a look into just what we're getting into in these last sections while it works on saving. There we go. Now, finally, section 7.4, this is the penultimate section in chapter 7 on number theory. It culminates in section 7.5, on cryptography, the RSA, public key encryption decryption system. The way it gets there is kind of interesting. We're putting everything we've been working on in chapter 7 together now, but there's one operation that's missing from section 7.2, like we both don't need to scroll. From section 7.2, we have a nice list of statements in modular arithmetic, and these are the statements that you can take a plus b mod k in this particular way. We did it with integers like we did down below here, but all these properties become really, really powerful the moment there's an unknown. Maybe a is unknown, for example, and we happen to know the value of all this, or maybe we're working abstractly and try to build up a system, and these are meant to be unknowns. This gives us a lot of powerful tools. But what will give us even more powerful tools is finding out how to divide. That's what the multiplicative inverse is all about. And the real numbers, if we're going to say divide by 3, it's just equivalent to multiply by 3 inverse. It's a weird way to say it, but if you have 3 by 3 inverse like that, using laws of exponents, you would get the right division. So we're going to try to redo that same kind of idea here. What we're trying to put in is a new statement about division, but we can't say a divided by b mod k necessarily. We have to reframe it as multiplying by a multiplicative inverse. If you're taking linear algebra, we use this as an analogy. It's the same kind of idea. You can't take a matrix A times a matrix B, or excuse me, let me back up on that. You can't take a matrix A divided by a matrix B, but you can take a matrix A multiplied by B's inverse, if an inverse existed. That's another problem. You have to know when the inverse exists. So as we go through these notes, this is the theorem that's going to provide it for us. And it's also going to provide us another algorithm. This one's nowhere near as bad as the Chinese remainder theorems that we're getting through. But it will give us an inverse inside of ZP as a guaranteed statement, provided we know that we have relatively prime between A and N. Or if P is prime outright, then everything inside of ZP is automatically relatively prime. So this will guarantee us an inverse. But to really see how this works, we have to know how do inverses actually work inside of ZP because it's a new algebraic system. So that's what the notes above are all about. Once we get through this process, we're now on Fermat's little theorem, and it's not too hard to demonstrate how it works just by this simple example. But what's impressive about it is how it ties into crypto systems, like the widely backbone internet security system, the Rivest-Shamir-Alderman algorithm. So this Fermat's little theorem and the rest of our algorithms all tie in. If you're curious on how that works, I wrote in this information. I won't go through this line by line in class. Think of this as just mostly a summary for just you to take a look at too. If you're curious how all these things stitch together, these are the major components of getting and working on that RSA decryption calculations. Turns out the Chinese remainder theorem isn't fully necessary, but it is to speed up the process of decrypting calculations. So that's kind of interesting in a way. We could have skipped this, but now that we've done it, we can be informed on how to make RSA decryption even faster. So that's the tour of the notes. The notes really end on this problem, and everything down below just further information. Where we have to start is all the way up the top with multiplicative inverses, multiplicative identities. Any questions before we launch into the notes starting here? Okay, well, some algebra about the real number system is this first block right here. Nothing's too serious, not a question that would ever come back. That's why the example isn't numbered, but just a way to set the analogies that we're about to set up. We're going to think of one as a multiplicative identity only because it has this particular algebraic property. 1 times x returns x for every value x in the real number system. So that's what gives us an identity. Nothing changes through the action of multiplication. Whatever we put in, we get right back. Once we have a multiplicative identity, the major thing that these notes are about are the multiplicative inverses. So like our author mentions in the reading for this section, it's a good idea to do this in the real number system, even though we're really, really good at real numbers. because we're going to the new algebraic system ZK, and that's where things are a little bit different. Multiplication is different, and finding an inverse is a lot different. So first, the multiplicative inverse of x in the real number system. Notice we automatically deleted 0 from that set of numbers. We don't have an inverse for 0 in that system, but it'll be denoted this way, x inverse. Or 1 over x you could write, but we're going to avoid that since we cannot do 1 over a inside this set down below. All the multiplicative inverse has to do is, when we multiply x by its multiplicative inverse, we have to get the multiplicative identity back. So algebraically, this is what we're trying to achieve inside of ZK, that system down below here. Well, that's the definition. And so now it says the problem of dividing can now be reframed as multiplying by multiplicative inverse. Here's the interesting part of the problem. It says find the multiplicative inverse of 5 in R. Again, we're really good at this, so think of this silly kind of problem just as an analogy to go forward. We'll write in 5 inverse is 1/5. We eventually have to write in the fraction, so here it is. Guess we could have gotten away with that with properties of exponents, but let's continue on this way. We'll say 5 inverse equals 5 since, or 5 inverse equals 1/5. I just heard that missaid statement. Since 5 times 5 inverse equals, well, let's actually go that route with exponent laws. We didn't necessarily have to write in 1/5. We could have written in, this is 5 to the power of 1 minus 1. Power 1 came from the first factor, negative 1 came from the second factor. This is now 5 power 0. It does return the multiplicative identity, and so it tells us we had the right inverse right over here. Even though we didn't use the fraction 1/5, we could have and gotten the same result. Well, any questions, folks, on that analogy here? Okay, going forward, here's our next interesting thing that's going to happen. Instead of using the real number system where we have really great knowledge on how everything works, we're now going to ZK. So this is going to be a set of numbers that are the outputs of taking every single integer mod k. Every integer mod k is going to fall into this set from 0, 1 through k minus 1. Even if you take negative integers, they fall right inside that set. So we're referring to a constraint of the form x mod n as a congruence, x mod n equals a rather. And then these notes, and this can be written in a lot of different ways. X mod n equals a can also be written, thinking back in section 7.2, as x is equivalent to n mod a. The author in this chapter goes back and forwards on that kind of notation. Maybe the idea is just to get us familiar with both ways of denoting x mod n equals a. We could also say x is just equivalent to a mod n. So now in this system, like we mentioned, things run a little bit different. If n is greater than or equal to 2, and a is in Zn, any possible integer in Zn, we'll say the multiplicative inverse of a in Zn is still going to be denoted a inverse, like what we did above right here, and it has to have this property. A times a inverse, much like the 5 times 5 inverse, will be equivalent mod n to 1. Essentially what we said here is 1 is the multiplicative identity in the set ZK. Let's say that in just to make it a solid statement. This 1 is the multiplicative identity in the real number system R, but also in Z, and this definition it's Zn rather than ZK. That's kind of jarring. So we have a multiplicative identity, and that's all the multiplicative inverse has to achieve. Multiply it against A, do mod n, we have to return to 1. One thing that can happen that's kind of interesting is it's possible that there is no element x such that A times X mod n equals 1 in Zn. If nothing in Zn multiplies against A down here, returning back to the multiplicative identity, then we'll say A inverse doesn't exist or is undefined. Either way would be a valid way to say it. So that's our full new definition. Now we're going to start testing it out on examples that build up and up until we get just a new algorithm for guaranteed computation of an inverse when it does exist and conditions on when it would not exist. Well, any questions at the moment, folks, with the core definition above? Okay, let's do a couple verifications then. So what we're doing in part A is not too different than we did up here on the example that's acting as an analogy. The claim is that 5 inverse is 3 in Zn. The way to check is we have to take 5 inverse, so that the value that's going to go there, and multiply it against the A value that we're looking for. That might be too much color coding for this. So let's say the A value that we're interested in is just going to be 5 itself. Again, think of by analogy up here. If 5 inverse is equal to 3, then we should be able to take 5 times 5 inverse, work through this statement, much like what we're doing up here, result in a 1. And if that happens, then this equation above is true. So very similar to what we did above, but now we're working in a whole new algebraic system, ZK. So the way we actually compute is totally different now. Let's rewrite this as being equivalent mod 7 coming from this spot over here, to 5 times 3. I didn't do too much. All I've done now is replaced 5 inverse by substitution with its definition, 3, which was kind of like what's going over here. 5 inverse can be redefined as a 1/5. So now this will be equal to 15. I wrote this as just an equality because I did an ordinary multiplication here. I wrote this as an equivalence mod 7 because I used an equation that is only valid in Z7 itself. So the notation is a little bit weird as we run through this. But now when we get 15, we want to know what that's equal to mod 7. 15 mod 7, well, 2 by 7 is 14. That means 15 mod 7 is a 1. So we're using essentially this kind of notation, going back and forth as the definitions or the problems get stated. That looks like a purple bar rather than the number 1 for some reason, but that looks a little bit more natural, like a number 1. We get the 1 as a result, and that's the verification. 5 inverse really is 3, because when we take 5 by 3, mod 7, we get a 1 directly, landing on the multiplicative identity. So we'll say here, this implies 5 inverse equals 3 in Z7. So weird way to divide by. We can't really divide by anything. We just keep saying that as the analogy that we're trying to convey here. Division is really now algebraically multiplication by the inverse. We're using this analogy of the real number system, but it's definitely pretty weird so far. Well, any questions, folks, on our first computation? Okay, part B gets weirder still when we're looking into this one next. Here we're inside Z4. This one's weird enough. Let's list out Z4. Z4 is the set of every integer mod 4. And the only integers you get mod 4 from the full set of integers is 0, 1, and 3. So that's our new algebraic set to work with. It has all sorts of interesting operations, like say these 4 right here. And also we're trying to develop multiplication by an inverse. But this one's weird. It's saying 2 inverse does not exist in this set. It's just flat out undefined. We have to explain why. it says show that, and really the only way to explain why is by following, say, this kind of analogy. If we didn't know what 5 inverse was inside Z7, let's rewrite Z7 just for something to look at. Okay, so here's our Z7. If we never knew 5 inverse was 3, what we would have had to have done is, right in this position, start checking values. Take 5 by 1 mod 7. That's still 5. Notice I skipped the 0 because 5 times 0 mod 7 is still just a 0. Then we would check at a 2. 5 times 2 mod 7, that's going to be a 3, so still not there. Then we would check at a 3. And that's where we landed on this one. So we can just do an exhaustive search until we find the inverse. That's not the ultimate goal of section 7.4. We want to compute them in a more smart way. But an exhaustive search is helpful down here to show 2 inverse does not exist. We'll do the exhaustive search by taking 2, multiply it against the elements. I seem to have forgotten a number there. Let me go 0, 1, 2, and 3. Multiply it against the elements now that they're all there. And if we get a 1, there's a problem with the way the problem is written. We're expecting never to see the multiplicative identity. And that's why 2 inverse just can't exist in this set. So let's give this a try. We skip 0 because 2 times 0 is 0, then 0 mod anything is back to 0. We might skip the 1, but let's run it in anyways. 2 times 1 is equal to 2, and it's equivalent mod 4 to 2, since 2 mod 4 is still just 2. So no luck on the 1, but we just move on down the line. So try it with a 2 next. 2 times 2 is 4, and 4 mod 4 is 0, or 4 is equivalent to 0 mod 4. So still didn't hit the multiplicative identity. We just go down the line and try the next value. This is the only other one to try, so go 2 times 3. This will be 6. And 6 mod 4 is back to 2. We never tried the 0, that's one we can skip. But for all other values, we never equal 1. And so we'll say here, since 2 times x mod 4 never results in a 1, which is the multiplicative identity, this means 2 inverse does not exist. Or you can say it's undefined, or you can write that shortcut from calculus where you say just DNE for does not exist. That'd be well understood here as well. But that's the way to see if something does exist as an inverse, just as a check. Really, it's just a way to work through the definition and get a feel for what we mean by inverse. And this is how we can tell that there is no inverse in the set whatsoever. Kind of shocking. Well, one thing you might have noticed about this set, however, well, really both part A and part B, is that 5 is special. 5 and 7 are both primes, so they're automatically relatively prime since they're different primes. And 2, the 2 we're working with here, and 4 are also special. They are not relatively prime. They have a greatest common factor, which is 2. That's really the whole reason why we couldn't find an inverse. And that's where the notes is trying to get into. We want to look into relative primality once again, call the Euclidean algorithms again to check if they are relatively prime, because that's the condition on which we get an inverse. It's not how we compute it, but it's getting us closer to finding the right check before we do a large exhaustive search like this one. Well, let's take another look into just dealing with the set Z4 or Z7 on the next problem for our example 2. Any questions at the moment before we try out this new problem? Okay, so we want a full multiplication table for Z5. This gives us basically everything. We're going to lay out which elements of Z5 actually have an inverse, what their inverses are, And what is the result of multiplying any element of Z5 against any other element? We'll just know the full algebraic structure of Z5 the moment we write in the multiplication table. So here's how it goes. First thing you definitely want to do on this kind of problem is just physically write down Z5. This helps kind of set the space that we're about to put in. It's 0, 1, 2, 3, and 4. Double checking I didn't skip an integer. So we've got our Z5 laid out. Now it is a actual honest to goodness table, so we need to construct a table next. We have 5 elements going one way, 5 elements going another way. So a 5 by 5 table should do the job for us. This might feel a little bit like truth tables, but different values going inside the cells of the table. So first, let's go maybe a structure like this. 0, 1, 2, 3, and then 4. Then again, going this way as columns. Okay, can never seem to make these the same length, but that'll do as a table for us. It's an odd table. There's a lot to say about this, so we're going to leave our official answer right here, but make comments on what we're doing down below. So here's the comments on how you fill out a multiplication table like this. So this is a table in Z5. Let me just reduplicate that for extra emphasis. And let's just pick a random cell, basically. If we can pick a random cell, we'll know how to generate the whole table. Let's go for maybe that one. If we were going to fill in this cell right here, all we need to do is put in the operation of 3 times 3 mod 5. So 3 times 3 mod 5. Forget that that's not a subscript, using it this way to indicate modular arithmetic. Becomes 9 mod 5. And then finally, 9 mod 5 is a 4. Because Z5 is 0, 1, 2, 3, 4. These are the only entries that are going to propagate the table down below. So we just do the modular arithmetic, take the row value, the column value, multiply, do mod 5. Once we get 4, it just plugs in right here. So that's the process of getting the table filled in. And I think the arrows make more sense going this way. To fill in the table, we start with the modular arithmetic here, mod 5, and whatever result we get, we just plug right in. So that's going to be the name of the game of filling out the table. Any questions before we go and do the one in full? Okay, because the values here aren't very large, and we're doing this mod 5, it's a lot faster than you might think. For example, let's do the 0 row going this way. 0 times 0 is 0, and 0 mod 5 is just 0. We have a pattern here. 0 times 1 is 0. 0 mod 5 is just 0 again. Essentially, anywhere a 0 occurs on a row or column, everything is wiped out and just returns zeros. So this entire row, all the way to the right, 4 is 0. This entire column going all the way down is 0 as well. And that's a pretty good start. The 0 row, the 0 column is basically a freebie. The 1 row, the 1 column is the next freebie. So there's a lot of things we really don't have to calculate thinking too hard, because if we were going down this row, in this cell, go to the left, it's 1, go up, it's 1. 1 times 1 is 1, and 1 times 1 is equivalent to 1 mod 5, so no change. 1 times 2 is 2, mod 5 is still 2. And that's the pattern. If we're multiplying by 1, taking mod 5 doesn't change the value. 1 times 3 mod 5 is still 3. 1 times 4 is 4, mod 5 is still 4. So this entire row is for free. We just need to know it's the same values duplicated from above. Likewise, the column is for free going this way. It's the same values on the left. Here you take 2 times 1, but 2 times 1 mod 4 is, mod 5 is just a 2. 3 times 1 is 3, and it's equivalent to 3 mod 5, and so on down the line. Really, there's just 6 cells where it's a little bit more of a non-trivial computation. So let's carefully track through these remaining 6. I'm going to freeze the row value and then vary across the column. So in this entry right here, it's 4 times 4. 2 times 2, which is a 4 mod 5, giving us a 1. We're writing down the full multiplication table, and we're using it to find all values for which an inverse exists. But this is already one big giveaway. Just trying to find a color. Let's go with this color right here. All values in Z5 for which an inverse exists, it's going to be wherever we find a value of 1. I should have highlighted that one as well. 1 is invertible. Its inverse is 1. And, well, this isn't saying that 1 is invertible. It's saying 2 is invertible over here. 2 inverse exists, and its inverse is 2, is what this is describing. So let's continue to go through this row, but any questions so far with the table nearly done? Okay, so last row going this way is 2 times 3 for a 6 mod 5. 6 mod 5 results in a 1. So we get some inverses from that cell as well. And then next multiplication, 2 by 4 is 8. 8 mod 5 is a 3. So no inverses here, but we continue going on down this next row. So now I'm taking 3 times whatever the column value is above the red dot, doing mod 5. And on this one, this is 6 mod 5 for a 1. But notice we kind of already did that. Here it's 2 by 3, which is 6 mod 5 for a 1. There's a lot of symmetry in this table. So you can take advantage of the symmetry to fill it out faster. But we're doing some pretty small examples. It might be a good idea to just crank it all out and see if we didn't make a mistake, and then see if the symmetry really exists afterwards. So we got a 1 value there, and then we just move down the line. Here it's 3 times 3. So we have a value 9, and 9 mod 5 is a 4. Moving over, this is 3 by 4, so 12. 12 mod 5 is a 2. No inverses beyond this one right here. But here's kind of like that line of symmetry we're seeing so far. Anything on this middle line right here is going to be an inverse. But if we are across the middle line, you should go the same amount of cells to the right to get to the same inverse over here. So that's kind of visually striking once we put it all down on paper. You should see that same pattern when you do the same kind of work in the homework. So let's vary what is fixed. 4 from the last row, this is row 5 is now fixed. We take 4 by 2 for an 8. 8 mod 5 is 3. But notice that 3 matches by symmetry with the one up there. 4 by 3 is 12. 12 mod 5 is a 2. Through symmetry, we have a match going this way as well. And 4 times 4 is 16. That's the largest value we've gotten. 16 mod 5 is a 1. So another value there. And at this point, we're looking for which inverses actually exist. Any questions first, folks? Filling out the multiplication table?
I think you might have made a mistake on your 2 times 2, because you said 4 mod 5 is 1.
Oh, right. That 4 mod 5 is still 4. Thanks for fixing that one. Right there on the red dot, 2 by 2 is a 4 and just stays as a 4. Good eye on that one. Makes me paranoid. There might be other weird oddities in here. Anyone see any different ones that could be a problem?
No, I don't think so.
Okay. Looks like I was doing a micro sleep right about there. Good eye on that one. So now finding the inverses is just a matter of go to where a 1 occurred. This is saying 1 times 1 mod 5 gives you a multiplicative identity. And same for all these locations. So 3 times 2 will give us the multiplicative identity. So does 3 times 2 going this way. So not as many values as you might think. And here, what this is saying is 4 is its own inverse. So you can possibly end the question just by saying the inverses are 1, 3, 1, 2, 3, and 4. Never highlighted that 2 there. Everything is invertible in this set except for 0. We don't expect that one to be invertible. It's not invertible in the real number system, certainly. It's not invertible in Z5 either. Everything has an inverse other than 0. So let's end the problem by saying the inverses are 1, 2, 3, and 4. Every one of these values can be inverted, but we might have expected that because 5 is prime. We take a prime number and write out Z5, all the numbers that go inside are less than 5. That means there's no multiple 5 whatsoever. 5 itself is not in the set. Everything inside here is relatively prime to 5. That's what broke down over here. We tried to find 2 inverse in Z4, but the 2 and the 4 are not relatively prime. Inverse did not exist in this set. 2 has no inverse. But if you do a set like this with a prime right in this spot, every element other than the 0 element is invertible. Maybe another way to answer this question is you might have written it this way. Let's say i.e. if the inverses, or let me rewrite this. The values for which inverses exist, to try and match it up to the actual question, are 1, 2, 3, 4. And down below, I'm just writing down what are the inverses. One inverse is 1, since 1 times 1 comes out as a 1. 2 inverse is 3. Then go down to this one. 3 inverse is, go to where we get the 1. It's from the 2. And then finally, 4 inverse is itself. So that's what the actual values of the inverses actually are. And here we're just saying all the inverses exist. If you ended the question right here, that would have been fine as well. So that's our interesting algebraic structure Z5 with a lot going on with it. What we now want to do is find all inverses like this, actually be able to compute them in a really fast, reasonable way, not by exhaustively listing out the entire multiplicative structure of ZP like we did here. But this is just another way to look into what's going on with multiplication and another way to study the inverses again. That's why we're doing this problem here. Well, any last questions at all, folks, with this example 2?
Professor, up above in part A, can you explain how you came to 5, -3, or 5 inverse 3 again?
Oh, this part right here?
Yes, sir.
Gotcha. This part right here was pretty much just provided to us. So it was just a given statement in the problem. But then what it allowed us to do is, from 5 inverse right here, all we did was we made a substitution to get that value.
Oh, sorry.
But
Let me clarify. The 5 -3 at the end, what that you're implying after the highlighted one there. How did you come up with the -3 there?
that's a great question. That one looks like a typo to me. That should have said, I think I was trying to wrap up the last equation, but it should have said 5 inverse going that way.
Oh, okay.
Sorry for that confusion there.
No worries. Thank you.
Absolutely. Everything matters when you're in a new algebraic structure. So that's a really important clarification. Thanks for mentioning it. Other questions at the moment? Okay, so we have some really great hints on when you can find an inverse and when the set has lots of inverses, -0, which is never invertible. So now finally, we're going to turn this around and just tie together our observations. First is theorem 7.24. It tells us when you can get a multiplicative inverse. We have n is bigger or equal to 2 to form out our Zn so that the set isn't too simple. Take any element A inside there, and A inverse will exist. But that happens. Notice this is an if and only if. That's really helpful for us. Logic goes two ways on this one. It's a biconditional now. If only if the value n and the value a happen to be relatively prime. So that's what we've been observing all along in the notes, that this will allow us to get an inverse. And so if relatively prime comes into play, that means we could call in things like the extended Euclidean algorithm, because the extended algorithm, let's see here, doesn't quite say what it returns on this, but let's write it in. The extended Euclidean algorithm, oh, I think it does actually sort of right here. It gives us those values. Well, maybe not super helpful. Let's say it again over here. Extended Euclid returns x, y, and we call the last value r. It's being called d this time, so let's run with it. Makes sense, it's going to be a divisor. So now d equals the greatest common divisor of m, or rather a and n. We're sending a and n to the extended Euclidean algorithm. It returns the x value, the y value. We'll be working with the x. Curiously, we're not working with y on this one, but we get it from the return call. But we get to d, the greatest common divisor. This is relative to us now because we can say n and a are relatively prime, means this happens. an relatively prime. This is another if and only if, just like the one above right here. If and only if the greatest common divisor of a and n is exactly 1. So the extended Euclidean algorithm is going to check this for us immediately. It's going to see if we get a 1 out. And look how the function call runs. If d equals 1, we return x mod n. And that's going to be the solution to the inverse. It's just that. We can call mod and div algorithm to get that value quickly. But if the common divisor is not 1, we're looking into theorem 7.24, which says this is an if and only if. Not relatively prime means d is not equal to 1. So we go to the return call. No inverse for a exists. And that's appropriate because this is now logical equivalence. If this side is false, a and n are not relatively prime, this side is false as well. A inverse does not exist at this point. So that's the essence of the return call. We'll have a inverse, and it's this return. When they are relatively prime, common divisor is 1. If the common divisor is anything else, we'll just essentially cite theorem 7.24 and tell the user of this algorithm there is no inverse. Then corollary 7.25 is nice. It's just a side effect. If you take a number p and its prime, every single a inside zp is going to be relatively prime with p itself. So every non-zero a and zp will automatically have a multiplicative inverse. It'll run through here and never hit the else call. It'll just correctly give us the inverse right away on that line. So it's a pretty fast implementation. I think we've got about 15 minutes to give it a try. We'll implement it here, practice with it with the time we've got, and that'll probably take us to the last bit of class so far. But any questions at the moment? Okay, let's see if we can run this. It says implement the pseudocode in a programming language of your choice. This pseudocode is not as dense as like the extended Euclidean algorithm or the Chinese remainder theorems. This one is pretty decent as pseudocode itself. So let's write it in directly. into this environment. Again, it's the understanding you're probably going to be using your favorite programming language of choice. It could be this if it's just convenient for this class, or any other kind of language. Let's start with, well, input and output is a good description of what we're about to do. Let's start there, and that can help us think about the algorithm we're about to write. So input is going to be an A in Zn, and n has to be greater than or equal to 2. Space there just so it doesn't look like an arrow. I'm not sure if that helps. It's not easy to write in that kind of stuff as a comment here. What we want to output is A inverse in Zn if it exists. And I guess essentially a statement if it doesn't exist. So we'll call this inverse. In this particular language, the function structure with the inputs an goes on this part. Now, let's take a look at how we're going to maneuver through this. We make an immediate call to the extended Euclidean algorithm. It's posted here under the Chapter 7 algorithms. You can copy paste from here if you're using RStudio, or treat this as actual pseudocode itself to implement into your language of choice. So this is a pretty nice function. It has a little bit of error checking built inside of it. And coming back down to this, let's do the function call right here. I'm going to store as an intermediate result. Let's call it literally the result that like we've been doing. Extended, Euclidean, and we send to it the inputs an. Now we need some results. This is kind of curious again. We never actually use y if you look at this pseudocode really, really closely. Sure, it's part of what the extended Euclidean algorithm wanted to achieve with the y value there, but never used. We just need the x value and the d value. So x is going to be assigned result 1. These are thankfully in order. X is the first part of the return on the extended Euclidean. Y is the second part. D is going to be the third part. So D will get result 3. So now that we get through there, this is pretty much the end of the function. 2 returns depending on if it's relatively prime or not. So we'll say if D is identically equal to 1, return x mod n. Let's cite our one function, mod n div, x n, and bracket 1 just to get the modulus part. So that solidifies this return. And here we can just give a warning to the user like we mentioned. We'll say else. Return. No inverse exists. Or any kind of statement that makes sense here. You might say A and N are not relatively prime. Something like that could be part of your return value here. This should do the job for us, but let's give this a try first by running it. No errors occurred, so at least it's implemented as a function inside this language. Now we wonder if it works. Let's test it out in some known values. Maybe before flying off to the other part of the document. Any questions or comments with how the statements are laid out? Does it look like we've missed anything or anything that could be better ran? Okay, let's try it out next. This is the moment of truth. We're going to call inverse an. Let's try it out. You can try out a bunch of stuff right here. For example, we could try to find the inverse of 2, but let's go up here where it's a little bit easier to see on these simpler examples exactly what we're doing. So first call is going to be inverse. We're trying to find the inverse of 5. So throw that in first. But we're doing this in a specific algebraic system, Z7. So that's the n part where we're doing mod n, it's mod 7. The a part is the thing that we're trying to invert. So we just put in the 5. Inverse 5, 7 gives us, hey, it worked. It gives us a 3. It's kind of nice. And let's try it out again. This is no guarantee it's working literally correctly. Let's see if it inverts for 2. So throw a 2 inside there. Recall we said there is no inverse for 2 because every value x we multiplied against never took us to a 1, mod 4. So now really looking into this, at least through this new algorithm, inverse 2, 7, well, that would work, but I didn't put in the right value that we're modding by. We're doing a mod 4. Because 7 is prime, we'll always get an inverse for any value 1, 2, 3, up to 7. But if we fix this and do what we intended to do, invert 2 in Z4, we get the message no inverse exists. That's because the greatest common divisor between 2 and 4 is 2 itself. They weren't relatively prime. So D equals 1 was never triggered in the syntax. So now we have a really, really fast way to compute inverses. That's kind of nice. We don't have to work so hard by bringing out the paper and pen modular arithmetic like this. Essentially, we are now able to put in a new process here that we can do multiplication by inverse, the spiritual division part of the modular arithmetic. So we implemented the code. We didn't do much with this, but might as well just share it right here. I'll put it in the same document, but here is the R syntax. This does copy paste outside of Word document just fine. But I think we've mentioned this before, you would never want to write inside the Word document. Many tiny little, very hard to find errors could pop up. Okay, let's try this out. Using inverse AN, compute A inverse in Z6 for all A in Z6, for which A has a multiplicative inverse. Now that's a bigger problem because 6 is not a prime number, and plenty of the numbers inside Z6 are not going to be relatively prime with 6. So you could do this problem in a different way. You could come up here and build out a multiplication table to solve this. But now we have a really slick tool. We can just come down here. Let's write out Z6 just as a nice reference point before we start. Z6 is 0, 1, 2, 3, 4, and 5. We might want to be cautious with the way we wrote this code. There is not a lot of error checking whatsoever. And if we try to pass a 0 to this, we might actually make it break. Let's try seeing if we can invert 0. Inverse 0. This makes me nervous, and we're doing this in Z6. So 6 is the last input. It starts working. What did it do? It went into the extended Euclidean algorithm, and it's doing something there. I actually expected some kind of Stack Overflow error at this point. Inside the extended Euclidean algorithm, we didn't do a lot of error checking either. Oh, and it won't show us the function while that's running. Here's the extended algorithm, and let's see, we had to have n greater than or equal to m. We're doing modular arithmetic. And if something returns a 0, n mod n, we'll return C10n. Interesting. I'm not too sure how it's getting hung up, but definitely has a problem at 0. Let's put here just to make this a little bit built up. If A is identically equal to 0, let's just immediately return 0 has no inverse. That looks like the letter O. 0 has no inverse in Zn. So another error right there, or another slight error check for that part. Now, if we try to do something we really shouldn't do, try to find an inverse of 0, that doesn't make sense in R, doesn't make sense here, we get the proper response. Let's take all this and just make sure it's incorporated. Okay, so no inverse for 0, but we're probably expecting that. we're to compute A inverse for all values which the inverse does exist, so we just skip across 0. 1 always has an inverse, and it's its own inverse. 1 times 1 mod anything is still just 1. But we're curious on how the syntax handles it, so let's see if it works. Yeah, it does the job for us. So we do have an inverse right here. We want to say what the inverse actually is. So it says compute A inverse. So here's us computing A inverse. 1 inverse is 1. So we move on down the line and see how our syntax handles. 2 is not invertible because between 2 and 6, the greatest common factor is 2. But still, we're just checking it out. That's what we are expecting. Same problem on 3. Same problem on 4. These were not relatively prime. The 5 is a prime number, less than 6. We should get an inverse on this one. It says 5 is its own inverse. So let's write down 5 inverse equals 5. I'm looking at my notation. Let me build it up a little bit better. Just to really specify, 1 inverse could be misinterpreted as an inverse in the real number system. 5 inverse can be worsely misinterpreted as an inverse in the real number system. But this is us saying we're talking specifically about the algebraic structure here. 5 inverse is equivalent to 5 mod 6. And that's just because 5 times 5 is 25. So 25 mod 6 is exactly a 1. So it's kind of satisfying to see our algorithm actually work this time. And it's actually using a lot of stuff. Extended Euclidean itself calls mod and div at the same time. So, well, with where we're at in the notes so far, we're at the so-called Fermat's little theorem, the last part or the last concept. This is a one we could try to do in 3 minutes and some change, but that's not a great way to learn this theorem. So we'll come back after the exam, a week away from today. So after our exam on the 22nd, or excuse me, our exam is on the 21st, still getting mixed up on Mondays and Wednesdays and Tuesdays. After we come back from our exam on the 21st, we'll be back on the 23rd, a week away from today. We'll finish out this theorem and then push forward into the cryptography section to see how all these weird algorithms start to really come together for something a little bit more useful than just doing that. But any last questions at all, folks, before we call it a night? Okay, well, that's all I have for folks today. As I'm getting into Friday, going into the weekend, I'm going to first be solving the second version of the sample exam problems down below here. Then I'm going to immediately convert into grading homework problems, particularly for these sections, trying to get them back to you as fast as possible. And standard comment is if you're working over the weekend, studying for exams or working on homework, I'll be very happy to help out. Don't hesitate to reach out to email. I'll get back to you for sure. But have a great weekend, folks. I'll see you all next class.